Very good evening to one and all present here. First, we regret with you participant that we cannot match with this time as of the previous guest. Mr. Sandeep was struggling with some network issues, so we regret from our side. And we'll go on. We like to go on with the next session of the session about with Dr. M. Kaliamoorthy. Dr. M. Kaliamoorthy is a professor from Dr. Mahaling College of Engineering Technology. He did his UG in KSR College, and he did his PG at Pondicherry Engineering College, and he is a gold medalist over there. And he continued to work as an senior technician, and then he went on with this professor of duty in Andhra Pradesh, and then he served his professor duty in PSNA CET, then to his professor duty in Karpagam College, and then he joined the year of 2016 in Dr. Mahaling College of Engineering.
Hello, can you hear me?
Sir?
Can you hear me?
Yes, sir. Yes, sir.
Yeah. Thank you, Professor Tony.
Yes, sir.
I would like to take this opportunity to thank all the organizers here for giving me a session to talk on this ATAL 1 week FTP on revolutionizing electric vehicle powertrains, the role of wide-bandgap semiconductors in overcoming challenges and shaping future trends. Sorry for delay because of the technical issue which has happened due to some sudden disturbances. So because of this, we could able to swap the sessions between 7:39 session is being delivered in an advance. That topic which I'm going to deliver you here is the last 2 days you have been looking into different types of wide bandgap semiconductor devices used in electric powertrains, especially on silicon carbide and gallium nitrate devices. You might have looked into the options of seeing that as a new upcoming devices or being used in few applications right now for miniaturization of converters and operating the converters at a very high frequency. Some of the advantages like this, but this session will give you an understanding of how to use those devices in the simulation aspect and understand how these devices will perform when you do the simulation. And once the simulation is done, then if you are satisfied with the results of the simulation, then we can go for making it as a hardware prototype as per our requirement is concerned. So this is what the ultimate agenda of this particular session. I'm going to give you a hands-on exercise on how to use this wide bandgap semiconductor devices in simulation by using LTspice. So the general overview of and functionalities of this simulation. Simulation are fast and accurate spice engine for circuit simulations, and it supports both transient AC, DC and noise analysis. It has vast library made of pre-made components. Suppliers, once they fabricate the device and make it to come into the market, you could able to see there are a lot of websites like Wolfspeed, DigiKey, where you could able to look into the models of the devices which is available in the market as a spice models. So there are lot of vast libraries available. Nowadays, all the analog devices or TI, whatever they make, immediately the spice model is also available for us to understand the simulation working of it before going into the hardware implementation. So the library is very vast. You could able to see lot of components available. Because of this, we could able to easily interface by creating circuit diagrams or the requirements whatever we have. We can also add a third-party component. It is not restricted to any particular manufacturers is concerned. You can add any third party because SPICE is a common platform where you could able to have all the type of simulation possibility is available. And the thermal simulation is also possible. We could able to see the temperatures of the junction, and we could also select the proper thermal cooling system for our converters are concerned. And it is a free tool. There is no limits to use. All the features, nodes, components, no such limits are available. Whereas there are certain tools like Plex, MATLAB, of course, there are a lot of features are there. Plex is one tool which is very costly. If you go for a free version, it has limited number of nodes to use it. And there are simply some other tools where we could have, if you look at the evaluation, I mean the free version of it, you could have a lot of limitations there. But this Spice is free, where we could able to use this at any point of time, LTspice especially. So why we need this simulation? First, we have to design and test the power electronic circuits, whatever we are trying to use it for electric vehicle application or any applications are concerned. And it allows us to test and refine circuit designs without the need of expensive physical prototypes. First, let us simulate the requirement as per our specifications. I will show you how to simulate a boost converter here in our exercise now. I will show you how to use the boost converter by using silicon carbide as a device. And based on that silicon carbide device, we could able to have some performance specification, and we'll see whether that performance specification is meeting our needs or not. We can test it before going for a hardware by using the simulation tools. That is what the ultimate interest of having that in the mind of this delivery is concerned, very specially. And easy to modify circuit components. As of simulations is concerned, I can easily modify the circuit components is concerned. I can easily go and change the parameters like inductance, resistance, capacitance. Say for example, I want to look into the duty cycle. If I want to change the duty cycle, what is going to happen on the performance, affect how the performance is going to affect because of changing the duty cycle. All that can be incorporated in our simulation tool itself. That is what the main ultimate advantages of having the simulation tools. And not only that, we can also have a understanding of how to use this, create a new ideas. For example, once we started simulating, we could understand the problems associated with it. Once if we started addressing the problems which is associated with the simulated converters are concerned, we can address the same problem, and we could able to develop some new ideas from it, and see that how that can be betterly addressed. So that is also another option of having that in the tools are concerned. So the ultimate interest of having all this is to create or to understand the already explored circuits. So that is what the ultimate interest of having this. Yeah. And those who are not right now using LTspice, here is the, because this is a group of mixed audience. Few might have been using LTspice, few might have not used LTspice. So I wanted to touch upon how to install LTspice and how to start using that. So initially I was thinking to have brush up of using installing it. Just it is a free tool. You can go to Analog Devices website, and I've given a link there. For the first time, if you go there, they may be asking for some registration. You can use this first time registration. Once you register, you can download the LTspice simulation software for the for your operating systems are concerned. Recently, they are supporting only for Windows 10 and above. Windows XP exe file is available, but it is out of support. They are not supporting us for any bugs are concerned. But for the higher versions of Windows, for above Windows 10, we could able to use the tool very effectively. Even for self-learning, it is not that, because there are many tools like LTspice. It is not that only LTspice. Of course, LTspice is also having a lot of instructional videos available in their website. You can go there, start getting started with the tutorials which is given in the instructional, in the analog devices website itself, and you can look into start from a simple circuit, and you can able to do lot of simulations by using this LTspice. That is what the another even after completing this session, you will understand only basics of making a small circuit in LTspice, but the same thing can be explored by yourself by having additional learning, self-learning, by using the instructional videos. That is what the ultimate interest of having those videos in the website. And it is a simple graphical user interface tool. Once you started browsing the once you started installing, once you installed the tool, you'll get a screen something like this. This is what, once it is open, once you open the LTspice, you'll get like this. This is what you could able to get from the click. So if I click this, this is something what we could able to see to create a new schematic. This, once you click this, it will lead to another screen like this. So this is where you could able to use the graphical user interface library, try to drag and drop whatever the component which is available in the library, and you can make use of that very easily. So this is what the another usage of this, this is what the next step of going into the LTspice. Once you go there, you could able to see the toolbar here. This is the toolbar. So the same thing I have put here in a bigger version. You could able to see there are a lot of tools available, and this is one which is what we call it as settings, and this is one to create a new, open, save, print, and this is used for transient analysis. What type of simulation you are going to do? Either you are going to go for a transient simulation, DC sweep, AC sweep, all that can be given in this type of simulation can be performed here, and I can use this button to run the simulation, and this is to stop it. This is all the different types of window alignment. Either I want to have two horizontal windows, vertical windows, all that. You could able to zoom this simulation, and this is to minimize, and this is to set to the window, and this is to shift the graph. You can able to see the waveforms in the form of a graph there. In the form of a waveforms, you could able to plot and see that. If I want to rearrange the waveforms, I can use of this. And if I want to remove certain things, say for example, there are two waveforms in the same graph, I want to remove one, I can make use of this. This is the wire, ground, this is wire, ground, and this is the voltmeter, and this is resistance, capacitance. These all tools are available. This is one which is what I call it as library. You can make use of this library and pick up the devices whatever you are required to, and these are all some of the commands which could able to give it for the simulation while working on the simulation. And this is to remove that. We want to move, stretch, search, undo, do, rotate, everything. This is for rotating. So all this we have. This tool is used for making schematic much simpler and much comfortable in the screen, to look more comfortable in the screen and try to do the simulations. So this is what about the tool. And let me try to go with a simple rectifier simulation without with and without filter, with and without C filter, and slowly we will move into the silicon carbide based boost converter application. So here, if you look at this is the schematic which I have drawn for diode rectifier. So this is the diode rectifier circuit. Diode rectifier, you could able to see this is a transformer which is made by using coupled inductors. So this is our coupled inductors. I made this by using, there is no separate transformer available in the LTspice, but still I can make use of the coupled inductor and make them to behave as a transformer. And I have 4 diodes here and a resistance of 100 ohms. So let us try to simulate this, and we could able to see after simulation, I could able to see the waveforms associated with the results. Here you could able to see this is the input node waveform. This is VN001 is a node at this point. I will show you once I started using the tool. So this particular point and this ground, what is the voltage appearing across this particular, this is BN001 node. Between this point and this ground, what is the load, what is the voltage that is appearing? That is what it is denoted in this green line. And this is the current through the resistor. You could be able to see the resistance. The current through this resistance is what it is shown here. And this VN003 and VN minus VN004, that is the voltage between this point and this point. This is VN003 minus VN004, and this red is the load voltage. This is VN002. This is VN002. I could able to show you via simulation. So let me stop here the presentation, show you the demo, and come back to the presentation again for better understanding. So let me go here. Without filter, you can able to see a rectified sine wave, whereas with filter, you could able to see that there is a the ripple in the output voltage is drastically reduced. So this is the charging instant of the capacitor, and this is the discharging of the capacitor. So you could able to see the ripple voltage is completely brought down. In the earlier one, I did not use a capacitor here, whereas here you could able to see there is a capacitor put on this. And as I told you that we are going to look into the boost converter simulation with the silicon carbide device. The specification of the boost converter which I am supposed to use here is a 250 watts boost converter with a supply voltage of 60 volt, and I am expecting an output voltage of 125 volts. My output voltage is 125, whereas the switching frequency, you could able to see that it is a high switching frequency of 50 kilohertz. Inductor is having a ripple of 10%, and the voltage capacitor, I mean the load voltage is permissible to have a ripple of 5%. With this design specifications, let us try to design the values of LNC which I am trying to use it in the circuit. And once that LNC value is decided, I can put it in the simulator and look into how to simulate it. So first let us try to design the parameters of the boost converter by using the primary basic equations. We know that the output voltage V out is supposed to be 125 volt and V in is supposed to be 60 volt. So the duty cycle of a boost converter is given by 1 minus V in divided by V out. This is V in divided by V out. So this is supposed to be 1 minus 60 divided by 125, which is approximately equal to 0.52. So the duty cycle to get an output voltage of 125 volt with a supply voltage of 60 volt is D equal to 0.52. So this is the first step that we generally do when we when we design a boost converter. So after that, what will be my load current? The output current will be equal to, we know the output voltage, and we know the power of the circuit. So based on these two, I can calculate my output current, something like what I'm trying to give it here. The output current is equal to, we know the power is 250 watts, and output voltage is supposed to be 125 volts. So this gives me the current of 2 amperes. So first step, we have designed the duty cycle, we have found out the duty cycle for the operation, and the second step is to find the current, load current I0. So this is supposed to be the load current. So the third step, let us try to find out the load resistance RL. We know the load current, how much it has to flow. We know the output voltage also, which is supposed to be 125. So from the fundamental Ohm's law, V equal to I into R equal to V by I. So this V is equal to 125 125 volt at the output, and I is supposed to be 2, so which gives me RL, that is the load resistance, is equals to 62.5 ohms. So this is the load resistance value. And what will be the inductor current at the input side? So when I try to look at the input side, inductor current at the input side is equals to IL. The inductor current is equals to power, which is equal to 250. Input voltage is supposed to be 60 volts. So 250 divided by 60. So the inductor current will be approximately 4.1667 amperes. So this is the inductor current. So once I found out the inductor current, then I want to know the delta IL, which is the inductor current ripple. As we seen from the specification of the boost converter design, it's moving. 1 second. Struck home. Let me come back again. Yeah. There is some small issue. Could you hear me? Can you
Yes,
hear
sir,
me?
we are able to hear you, sir.
Yeah. Thank you, sir.
Yes,
Thank you.
sir.
Thank you. We are calculating the inductor current. Inductor current is supposed to be, inductor current, we have calculated it as 4.1667 amperes, and the delta IL is we are given it as 10% of the inductor current. So 10% of 4.1667 is approximately, you could able to see it as 0.41667 amperes. This is delta IL. So the inductor current ripple is supposed to be 0.41667. The average value of the inductor current is 4.1667. Since the design spec says that 10% of IL, so this 10% of IL comes around 0.41667. So if I try to put it as a waveform here for better understanding, assume that this is the IL average. This is 4.1667 amperes. So the inductor current will go something like this. It will go something like this. So this is the maximum value of the inductor current, which is IL max, and this is supposed to be the minimum value of inductor current, which is IL minimum. And if you look at this portion, this is what we call it as a ripple. This is what I call it as delta IL. Delta IL is supposed what we have calculated here, which is 0.41667. Therefore, IL max equal to 4.1667 plus this delta IL by 2. So that is 0.41667 by 2, which comes around 4.3750 amperes. Similarly, the minimum value of the inductor current, how I can calculate the minimum value of the inductor current, IL minimum is equals to 4.1667 minus, because this is the average value. From this, I'm going to subtract this part, which is delta IL by 2. So this is 0.4167 by 2. So this gives me around 3.9583 amperes. So this is how the inductor current will swing when I use this values. So now let us try to find out the value of L to meet out this ripple, that is 0.41667 of the total current of inductor value. So to find out L value, I have to use V in. We know the expression for it, V in into the duty cycle divided by Fs into delta IL. Fs into delta IL. V in is 125, which already given in the spec, and duty cycle we have calculated as 0.52 based on the input and output, and the switch frequency of switching, it is 50 kilohertz, so 50 into 10 to the power of 3, and delta IL is what we have calculated here, which is 0.41667. So if I use this and find out the value of L, I get approximately 1.497 millihenries. So this is the value of L I'm supposed to use to get a ripple of this value. I hope you understand how to calculate this value of L. L equal to 1.497 millihenries. And the value of C, how to calculate the value of C? I out, that is the load current, average value into D divided by switching frequency Fs into the value of ripple voltage. Ripple voltage is given in the spec as 5%. If you look at the previous one, it is given as 5%. So the voltage at the output side is expected to be 125 volt is the output, of which 5%. So 5 by 100, which comes around, you will get able to see 6.25 volts. So this is supposed to be your delta V out. Delta V out is supposed to be this value. So load current, already we have calculated the value of load current. Load current is calculated as 2 amperes. So 2 into 0.52 divided by Fs is 50 into 10 to the power of 3 into 6.25, which is supposed to be value of C is equals to 3.33 microfarads. So if I use this value of C, then I could able to get the desired specifications. That is what it is given. I used a device which is what we call it as the silicon carbide device here. The device which is used here is a silicon carbide device which has been taken from Wolfspeed. Wolfspeed, you can just go there. I'll just show you right now. You can go and download and install and download the package Spice library from the Wolfspeed website and make use of this device into the LTspice simulator, and I can run this. I will show you. I'll just 1 second, give me 1 minute. I'll go there. I'll start the simulation. Can you hear me?
Yes,
Yeah.
sir.
Yeah, thank you. Now let us go to the LTspice. This is what once, let me close this and open it again for better thing. There is an LTspice installed. You could able to see a screen like this. Once you opened it and click for new schematic. Once you click the new schematic, you could able to see a screen like this. And this is what I said, the component library. Component library. If you click this, it could give you all the components which are available. This is what I said, vast library which is available. And I can make use of a simple, first let us give you a simple diode rectifier, and then I will go for the simulation of silicon carbide based boost converter. So to make use of this diode rectifier, let me, there are few options which is already available here. You can directly use this. First, let us go here. I want to, as I said already, there is no transformer available in the LTspice. So for which I am trying to use an inductor. I'm just going to click this inductor 2, which is having a dotted terminal here. Just place it on the screen and you can rotate it. You could able to see I can rotate. This is one end of the transformer and this is supposed to be the another end of the transformer. So I've taken two windings. This is supposed to be the primary winding and this is supposed to be the secondary winding. So now I am going to take a voltage source. I put a voltage source here and I'm going to connect this voltage source with the primary. So I have a wire. You can just press W also to take a wire. Once I press the W, you could able to see a small cursor comes out and you could just put it, drag it, connect it to the place wherever you require. So this is how I do it. I hope you understand how to connect it. Then on the other side, if you look at, I'll just, sorry. Yeah, 1 second. I connect it like this. Then yeah. Now I need 4 diodes on the other side to create a full bridge rectifier. So I take a diode, rotate it, keep it comfortably on the screen. 4 diodes, D1, D2, D3 and D4, 4 diodes. Now again I wire this, put a wire, connect between these two, this one and this one, D3 and D4, these two diodes. Again, sorry, wire, connect it like this. Yes. Now this inductor, this is a secondary of the transformer. This inductor, I'm going to connect it to this point, and this inductor, the other end of the winding is connected to the other point. Yes. Now I need a load, so for which I take a resistor. I take a resistor, put it here, put a wire like this. Yes. Yes. This is what the complete tool is completed. Now I need a ground. So press G, or you could able to see a ground there. You could able to see a ground here. So ground, you click it. This is the ground on the primary side, and this is supposed to be the ground on the secondary side. Wire it, ground here and ground here. Yeah, finished. Now I would like to do some few calculations here before I go into the simulation tool. So here you could able to see a source. If you right click the source, it will give you some values like this. If it is a DC source, I can take DC value directly. If it is an AC source, I will go to this advanced tab, and in the advanced tab you have an option of sign here. Give a sign. Offset, it is asking for few parameters here. It is asking for DC offset, amplitude, frequency, delay, theta, phi, number of cycles, etc. So DC offset value is 0. Amplitude is concerned, say for example, I need 230 volt DC. So I'm a 230 volt RMS. If I need 230 volt RMS, then I need 230 into root 2. So this looks approximately 325.56. Through 230 into root 2 is the peak value of the sine wave. The frequency is 50 hertz. I don't want any delay, theta and phi, everything is 0. So just plus OK, and this source will now create a sine wave whose amplitude, whose peak value is 325 and frequency is 50. I just drag this and keep it here somewhere. Yeah. Now the resistance value, let me give some 100 ohms here, resistance, you okay. Then I should have some sort of a coupling between this L1 and L2, because there are two inductances. Now these two inductances, as of the simulator is concerned, it is a separate inductors, but in a transformer, there should be some coupling between. Coupling is strong if the coefficient of coupling is 1. Coupling is weak if the coefficient of coupling is 0. Now it is actually 0. Coefficient of coupling is 0. Now what is that I have to do? I have to use a command. For giving command, you could able to see dot T in the toolbar. Clutch this dot toolbar. Press K, L1 space L2, and put a coupling coefficient of 1. Just keep it here. That's all. Now I hope everything is done. Now we have to simulate. To simulate, you have configuration analysis, which is very near to this play button. Click this configuration analysis. Go to transient analysis. For how much time I want to run this simulation? Say for example 100 milliseconds. So I put 100 EM. Where I want to stop the simulation, say for example, from where I want to store the data of the simulation. Say for example 920 milliseconds. From 920 milliseconds till 1000 milliseconds, I want to store the data. So I can do 920 milliseconds, okay, and you will get a command like this. You have put it here, and that's all. Now simulation is over. The schematic drawing is over. Now I can play this simulation. To play this, there is an error. L1. There should be a ground here. 1 second. Yeah. 1 second. The values of L1 and L2 is not given. So that is the another important view. But when I run this, it is asking for what is this L value. L value, I did not give any values of L for this L1 and L2. So right click on this, you could able to see the inductance value, 400 millihenry on the primary side and 1 millihenry on the secondary side. If I give this gives me a step down ratio of 325 to 12 volt, 325 to 12 volt approximately, 16 volt. How this calculation is being done, I will just take my slide and show it to you. Could you able to see my white screen? Can anyone?
Sir. Yes, sir.
Yeah, 1 second. Yeah. This N value is calculated the number of turns ratio, because I'm using a coupled inductor. I'm not using a coupled inductor. I'm just using the inductor. So the value of N is given by root of Ls by Lp. Ls is the secondary inductance and Lp is the primary inductance, which is equal to Ns by Np, which is equal to Vs by Vp. So this is the primary equation to find out. We know that in a transformer, the ratio of secondary to primary turns ratio is equal to secondary to primary voltage. So which is equal to root of secondary inductance by primary inductance. So here this is not known because we did not know, we don't have any transformer in the LTspice as I told you. So this is not known, but we know what is supposed to be my Vs and what is supposed to be my Vp. So if I square on both sides, I'll get this equation. So Ls by Lp, root of Ls by Lp is equals to Vs by Vp. Vs by Vp. If I square on both sides, I will get Ls by Lp whole square is equal, Ls by Lp is equals to Vs by Vp whole square. This is what I get. So Vs is the secondary voltage. Secondary voltage, say for example, I need 16 volt as a secondary value, and primary voltage already were given. It is 230 into root 2. Primary voltage. Secondary voltage is supposed to be 16 into root 2. So this, if I use it, 16 into root 2 divided by 230 into root 2 whole square, which is equal to Ls by Lp. So if we use this, Ls is equals to 16 by 230 whole square into Lp. So now let me assume that Lp is equals to 400 millihenries. So if I use this, I'll get Ls is equals to 1 millihenry. So this is how we calculated these values of L and C, Ls and Lp, and I substituted the same in this equation. Are you able to see this? This is how I given this value. Now let me run the simulation.
நான் அது ஃபீட்பேக் போற வரைக்கும் இந்த ஃபீட்பேக் போற வரைக்கும்
Participant kindly mute yourself.
The series resistance, there should be some small series resistance. Let me add series resistance. Both
ஆயில் பண்ணதுல ஒரு புள்ள கேட்டாங்க
values. Again, yes. Now again,
இருக்கு.
yeah. You could able to see now. If you this is the window where we could able to see the plots. And this side, if you look at, if I take the cursor to the point where I'm supposed to see the voltage or current, if you press here, if it's a voltage probe, if I press here, this will give me the voltage between this point and the ground. So let me try to put that. Yeah, there's a small mistake here. One second. This L1, L2, there are the coupling between two L1 and L2. Yeah, that is a mistake. Again, I run. Yeah, you could able to see the load voltage waveform, which is a rectified sine wave. Say for example, I want to add another plot. Add plot below and put this as a reference. Mark this as a reference and this voltage. Now you could able to see this is the voltage which is appearing across the secondary side of the transformer. So this is a simple circuit for diode rectifier is concerned. I have few things which has been already worked out for you. Let me show you, because of the want of time, I will show you the results of the simulation alone. This is the boost converter, which I told that, which is already made it. So here I used a silicon carbide device, and I could able to give an input voltage of, we can be able to see V in is 60 VGG is the gate voltage for the device, which is supposed to be 15 volt. The designed value of RL, L, C, whatever I will just given the presentation about designing the boost, values of inductors and capacitors, those values, whatever I calculated, the same values are given here, and I could able to run, let me run this simulation. Yeah, now it is looked at. The voltage and current waveforms of the boost converter are shown here. The simulation is running for nearly 10 milliseconds. You could able to see 10 milliseconds. If you remember the specification of the converter, boost converter, which we are trying to design, the inductor current is supposed to be, average value of the inductor current is supposed to be 4.1667 volts, and the voltage ripple is supposed to be 5% of 125. So here you could able to say, I could zoom this and show you the voltage. It is supposed to be 125, nearing 125.
Sir? Sir? I'm unable to hear you, sir.
Sir, not audible.
Sir,
Yes. Kaliamoorthy, sir?
sir, no, sir, not yet.
Hello, now?
Yes, sir.
Yes, sir. Now, okay.
Okay. Okay. Okay. Okay. Yeah, this inductor current, if you look at it, is very close to 4.167 amperes, which is what we have designed the value, and you could able to see the SPICE output log there. I could able to show you the ripple voltage. I hope you could able to see this text file. The ripple voltage is supposed to be 0.408. What we have calculated is 0.416. This is 0.408, and if you look at the voltage ripple, it is supposed to be 6.25. Voltage ripple as per the simulation is 6.22. So it is very close to the values whatever we have designed. This is a normal boost converter. Now I have another simulation for you to show. Let me run only 2 more simulations. So again, in this simulation, what is done is, again, a very same simulator, same boost converter, but here in the previous simulation, I just fixed the duty cycle. But here I'm going to vary the duty cycle. Look at this, set step param. This command, what it does is, it varies the duty cycle from 0.2 to 0.9 in the steps of 0.02. It starts from 0.2, D, the duty cycle vary from 0.2 till 0.9, the steps of 0.02. So approximately there will be some 36 or 38 values between this 0.2 to 0.9 in the step of 0.02. So for each duty cycle, it will calculate the load voltage and try to plot us. So let me run this. You could able to see there are 36. You run is 1, which means that it is taking the first value of D and trying to simulate. Now the run is 2. It is taking the second value of D and running the simulation. Like this, it will run for all the 36. Once all these 36 values of D is completed, we could able to see the values of each values load voltage at each step by using the log file. From there, I could able to plot what will be my gain of the inverter, gain of the boost converter for each values of duty cycle. Say for example, for duty cycle equal to 0.2, what is my gain? For duty cycle is equals to 0.202, what is my gain? Similarly, for duty cycle of 0.204, what is my gain? So in the steps of 0.02, it calculates and give me the gain values for all the duty cycles for 36 values, and it will give me to understand, it will give me the gain plot, which will make me to understand how this converter performs for different values of duty cycles. So now almost 22 D values are completed, 23 is running. It will take only a few more minutes to complete. Once we complete, we will show you how to use this gain plot. Wait for 2 minutes. Yeah, 31, very close. Yeah, last value is running. Yes, now completed. Now here in the view, if you go to SPICE output log, you see that it is starting from duty cycle is starting from 0.2, 0.22, 0.24 like this. It gives me till 0.9. Now the values of the average value for different steps, I mean for different duty cycles are also shown here. I could able to plot it just by adding the trace of gain. This is how the for 0.2 duty cycle, what is the gain? Gain increases at one particular value, the gain started decreasing because any circuit will have its own limitation. I cannot operate at infinite gain. So this particular converter, the maximum value is occurring at somewhere at 0.84 or 85 gain, 85 duty cycle. So this is one important point. Then I will show you another one. One more simulation I have. I made it boost converter with parasitics. So if you look at generally this DC source, the inductor, everything will be available on the PCB. The connection, the lines, the PCB routes which joins the supply voltage and the inductor will have an inductance by itself. Similarly, there will be a drain inductance, parasitics inductance between drain and the connecting lines. Similarly for source, similarly for gate. So all these are taken into effect, and I'm trying to plot this with respect to the real scenario. I mean real-time device, real-time how a PCB parasitics are also considered. Based on all this consideration, if I do the simulation, the same values of design parameters, but this value of inductance is added extra, this LG is added extra, this LD, which is the parasitics of the drain, parasitics of the source, parasitics of the gate, and this is the parasitics of the diode, and this is the body parasitics between the ground plane and the supply plane. All these are taken into consideration and running this simulation. If you look at it, takes very short time. You could able to see that because of this added parasitics, the drain to source voltage is supposed to be very flat curve, but there will be a ringing which causes additional EMI and EMC problems, which is very important to address. One of the biggest issue of this wide bandgap devices is it is much sensitive to EMI and EMC, which is much we have to address in that. So in that aspect, this simulation is being made ready. So for which I should have some sort of a filter between the source and the converter, which will avoid all these parasitics and which will make some sort of an impedance matching to cancel the parasitics effects. So that is another important point. So this is how the simulation has been run, and let me show you the drain to source voltage. Look at this spike. It's very dangerous as of EMI and EMC is concerned. You can able to see, which is not available when there is no parasitics effects are added. So this point is very important, which has to be addressed whenever we go for wide bandgap devices are concerned. That's all for today, because other speaker is waiting. Because of sudden change in swapping, I could not show you much. Anyhow, if time permits again, we will try to meet it again in the other way. Thank you for patient listening. Thank you. Any doubts, any clarifications? I'm here to answer.
Okay.
Hand right? Yes, madam. Yes.
My question is that, sir.
Yeah.
So, about the software, you use the new software. So, what is the big advantage more than the MATLAB?
Yeah, MATLAB, the advantage of this particular tool is it gives you a real-time simulation. You could be able to see from the manufacturer's website itself, the SPICE library of the particular component. If you are using that in the simulator, which means that you are using the directly component itself, which gives you the real effects of using the component in the real hardware. Whereas in the MATLAB, that provision is not there, but slowly in the recent versions, that is also being added in the MATLAB also.
So, what are the applications of this boost buck converters in EVs, especially for battery balancing?
Yes. You have to use it for battery balancing, battery management system, charging. But there should be a bidirectional power flow should be available. We can use bidirectional DC to DC converter. The boost converter which I given demo is not a bidirectional, but you have to use bidirectional for EV charging and all.
Okay.
Thank you, ma'am. Thank you. Deepak sir, any questions?
Participant, kindly mute yourself. If you have any doubts, you may unmute and may ask. Yes. Yes, participants, if you have any doubts, may unmute yourself and you may ask.
Deepak sir, you have queries? Raised up the hand.
Mr. Deepak, if you have any queries, you may ask. Okay, sir, I think there is no more queries.
Okay.
I have checked in chat box too, sir. No problem, sir. Thank you very much, Kaliamoorthy sir, for accepting our invite. And within, though it was a very short time, we didn't give you so much of a time, but swapping a session within a short time and making you to present. Sorry for our trouble, sir.
No
But you
issue,
have
sir.
provided us your valuable things.
All these are possible. I mean, all these are also whenever in the real environment this will happen. Anyhow, no worries. Thank you for the organizers for giving me opportunity to talk about this topic today. Thank you.
Thank you very much, sir. Thank you very much, sir. Participant, you may now fill the feedback forms. The feedback form will be available. Next session, Mr. Sandeep will be session 5. Actually, session we have swapped with the session. Session 5, Sandeep sir will be joining us by Sandeep sir. Shall we start, sir? I would like to officially welcome you. Shall I go ahead, sir?
Yeah. Yes, please.
Very good evening, participants. It's my absolute pleasure to extend a warm welcome to you all for this special occasion. Today, we are honored to have among us Dr. V. Sandeep, a visionary in the field of electrical engineering and renewable energy, whose contribution always significantly advanced research, innovation, and education in India and beyond. Dr. Sandeep, currently serving as Assistant Professor and Dean in Planning and Development at National Institute of Technology, Andhra Pradesh. Has an illustrious career marked by numerous achievements. With a PhD from the prestigious Indian Institute of Technology, Delhi, Dr. Sandeep has been instrumental in establishing the Common Research and Technology Development Hub in the renewable energy sector, a project funded by Government of India. His work in microgrid, smart grid, electric vehicles, and AI-driven energy system is paving the way for a sustainable future. Over the years, Dr. Sandeep has been recognized with several prestigious awards, including Gandhian Young Technological Innovation Award 2013, the APJ Abdul Kalam National Award 2017, and the IEEE India Council Outstanding Young Professional Award 2020, among many others. His dedication to mentoring students, organizing technical events, and promoting STEM education has inspired thousands of young minds across the country. Dr. Sandeep's leadership as chair of IEEE Plus Vizag Bay section has also been commendable, with the chapter receiving the IEEE PES High Performance Chapters in 2021 Program Award. And his contribution to research over 50 international journal, 50 conference journal, 2 patents reflects his strong knowledge in the research. I extend a heartfelt welcome to Dr. Sandeep. Now the session is all yours, sir.
Yeah. Thank you very much. I hope my voice is clear now. Yeah.
Yes, sir. Clear.
First of all, I would like to convey two things. Yeah. First one is, thank you very much, the faculty members of EEE Department of Mahalingam College in Tamil Nadu, for giving this wonderful opportunity to interact and then share my knowledge on this particular topic today, on particular and electric vehicles. And at the time, second point is sorry for inconvenience caused from my side. There was, audio issues. Finally, I resolved it. Okay. So now let me continue the session now. Yeah. So, okay. I hope my digital side is visible.
Yes, sir. You're visible, sir.
And I was right. Let me go ahead. So thank you. Actually, yeah, it's a good FDP program, and I listened to the previous session. Also, it was a hands-on session by the Professor Kaliamoorthy, and now other sessions also from industry part and resource persons and all. It's well organizing actually. So I congratulate the department up to play also in this regard. And today's my particular topic is for discussion is reliability concerns in wideband devices, and which are emerging in the power electronics area. And we will discuss a few points on switching, what are the switching losses and the voltage spikes and material robustness, because particularly first of all EV technology is getting emerging now, is it right? And in that, a lot of challenges, developments, and we have a lot of opportunities also. So let me, in this presentation, I made that way, first we will discuss some of the recent developments and where we will get the opportunity, and then we will move to this particular topic actually. So this is what I have framed it, and yeah, thank you for Professor, for giving this my introduction and all. So thank you. So generally, what you expect from any kind of FDPs, you will look for some new content of knowledge. You will also search for product ideas, and you can explore for new directions for future research. And then next is, if at all, if you are already into the research work, you can try for some improvements and all. Or of course, you can also get to know what are the publications, resources where we are collecting and then project for this knowledge sharing and all. And also sometimes you have the
Participants, it's a kind request.
kind of
Participants, it's a
interaction
kind
with the
request.
industry,
Mute your
industry
mic.
resource persons also as a part of this industry program. This how you will get a linkages with the domain expert. So this way you will get a multiple benefits when you generally if you attend any FDP program, any workshop, skill development actually. And this particular talk, it's inspired by the global developments, my teachers, students, and wherever they are working, many places, and I used to collect a lot of information and knowledge in various forms. And it's a continuous learning experience, learning and experience actually. And coming to today's, this lecture, let us discuss with some of the points, developments in EV and challenges, opportunities. Then we'll go with, wide gamut. Devices, semiconductor EV powertrains and advantages we'll discuss, and then reliability concerns, okay, and then where we'll discuss about switching loss, voltage types and robustness also. And finally, we'll discuss about any research academic opportunities in particular this emerging area. So now coming to just some of the brief general things also. What is the role of electrical engineers? What we do is we design and develop new technology. We generate, store, transmit, control and convert. And primarily we deal with energy and power. But nowadays actually we are also dealing with information data communication. This is what the changes happened actually. Every electrical engineering graduate or students or any young faculty or any kind of member who graduate from EEE, I think we should understand at this point after this is bringing interdisciplinary into electrical engineering. And what is a fundamental route in identifying any technology? Okay, so maybe for example, wideband devices, semiconductor device. So let us we need to analyze that what is the state of art or current status of that particular technology. Then try to understand what are the problems in existing technologies and method, and let us go with what is the future development scope for us actually. So this way one has to go with, then each work will be innovative or novel actually in that case. And next is we can see that electrical engineering also, it's a very beauty. We do have that it's interconnected in a sequence, all the four subsystems actually: generation, transmission, distribution, utilization, under which the students will study different subjects. And one thing two things you should observe, that the smart grid technologies can be implemented at any stage of power system. And another area is where microgrid, where local available energy resources, we can tap them and utilize for our. And electric vehicles, where we'll directly, it is connected to our utilization sector for charging application. Is it right? And finally, you should able to good at modeling, design, development, analysis, operation, control. And we have advantages the EEE branches actually, just for awareness of students and faculty. Faculty, we are already aware of it, but students, sometimes there is a question like why EEE is, I mean, how to justify the EEE branch is, good and compared to EC and computer. We have a lot of, interdisciplinary is possible, where it's possible when compared to, any other branches. So these are all examples I quoted. Okay. Anyway, I'm sharing my slides and you will get a full information there. And these are the areas where emerging, okay, including electric vehicles, okay, smart grid, microgrid, DC grid, energy storage. And also now people are talking about and implementing a lot of technologies like IoT based, machine learning, AI, blockchain, cloud computing, deep learning, all these things, and the big data also. So these are things actually you can choose project areas from it. And these are the emerging and future areas actually most of us aware of it. This is and we have a lot of applications in electrical engineering particularly. Of course, we can also, many of the things we can include them into electric vehicle applications also. And mathematics is computing is behind that actually. Okay. So now we can see that we'll discuss some of the development challenges and all. So then yeah. So now why electric vehicles? Okay, we have very good reasons like depletion of the oil, gap between the user and usage and production, and then we need to address the global impact and economy, energy. We need to get energy independence because for conventional vehicles we are importing the oil from other countries, and that we need to reduce it actually. And even if you see the transportation sector is going to be root cause sometimes why this something is increasing the market or something, it will end with transportation sector only. And definitely we can address the climate change, global warming, and less environment impacts and less noise. And then regenerative braking is advantage is electric vehicle and cheaper to run. If you are spending 5 rupees or 6 rupees to run 1 kilometer using conventional vehicle, so it is come down easily 1 rupee, 1 rupee 50 paisa with the. So that is kind of also the economic you get it. And we do have 5 recommendations for EVs actually. One is to maintain adoption of the electric vehicle. We need to lightweight vehicles and vehicles, and that is okay. But we need to go ahead, as early possible with buses and trucks also. Then we need to promote the adoption in the emerging and developing country. And at the same time, we need to create the EV infrastructure and smart. Otherwise, without that, we cannot, make the energy management of the EVs actually in the large scale. And of course, we need to see that there should be some sustainable EV supply chain after the sales. Okay, for conventional vehicle, there is a very good market after the sales actually for the in case of service, repair, whatever maintenance. But in case of EV, it's under very underdeveloped stage actually. This is one thing. And China is leading actually. After that, European countries, USA, actually we are negligible when compared to China. Until whatever targets is achieved and going to be achieved by China by 2050, I think nobody will able to cross their their achievements also. That kind of the achievement they have achieved already. And coming to charging infrastructure, we need to have this publicly available fast chargers are available, but unfortunately those are available in less quantity right now actually. That we need to make it focus on more actually. And many automobile OEM companies, they focused and then accelerating their EV plans. Actually, they have announced that this particular year we will commit for this much percentage of electric vehicles. We'll release it. And surprisingly, there are some companies already they have put the ban. Okay, for this particular year, we are stopping the IC engine production. So slowly in the future, we can see all the automobile companies they switch over to this electrification. And look at some of the basics actually. So generally, we have a source and then that will have called as a well and it will come to tank and then tank to wheel and then vehicle to miles. So this is how we see the overall performance of the any vehicle, including conventional vehicle. In conventional vehicle, we have many energy conversions will happen between the chemical, thermal, and mechanical. So if you have more energy conversions, what will happen? We lose the efficiency. That's what happening in IC engine also. So now IC engine is we cannot get the IC engine efficiency more than 50% in ideally in the market also, which is available. So now we have, because tank to wheel efficiency, when you count it, we need to see that fuel efficiency, engine efficiency, clutches, auxiliary system, gearbox, and finally, if you calculate that, it will obviously less than 50%. And there are many studies will tell us, engine efficiency losses itself, more than 60%. So what is alternative? Then we should eliminate the engine and then go with alternative source of energy. Maybe that is a battery. So that's the reason actually we can compare some of the, even with the hydrogen also, we have very good, battery driven is going to be more advantage and all actually. And as mentioned previously also, regenerative braking is getting advantage with the electric vehicles because whenever you apply the brake, generally it will go in the form of, that kinetic energy will go in heat form. So instead of going that the kinetic energy, we can convert into, mechanical energy and then mechanical energy will connect to electrical energy. Finally, it is stored in the battery in the chemical. So that's what the advantage with the electric vehicle Honda. And also definitely we can also majorly address the climate change and global warming issues also. And we have very good projections actually. By even 2040 onwards, we are going to give a very good competition for other developing countries also, even developed countries also. So India has a huge market in the place of electric vehicles, particularly fully electric vehicles, of course, plug-in hybrid electric vehicles also. We have mostly, possibly three kinds of EVs possible: hybrid, plug-in, and then fully. Whereas hybrid, maybe we don't have any plug-in option here since it is no plug-in. So limited size of the batteries can be accommodated through power electronics. We will connect to the motor and IC engine will be there anyway. So that will be driven by your conventional fuel, gas or diesel and this thing. And regenerative braking, during regenerative braking, this machine will work as a generator and then through power electronic will store the energy into battery. And in case of hybrid, we have series, parallel, combined these things. And already these models are commercialized. Okay, series you can find GM Volt, they patented and commercialized it. And parallel hybrid, we can see these two sources are connected parallelly. Holda inside you can find out. And Toyota series, you can find the combined series parallel also. So since other cases plug-in option is there, more you can accommodate more battery capacity actually that is possible here. And all electric, we don't have any, conventional fuel, and then we will connect driven by the completely battery, power electronics. And then, you have this, you can see the block diagram of battery, DC converter, inverter, and then motor, and then you will connect to mechanical axle of the wheels actually. Okay. And this is arrangement of the series hybrid vehicle. And this is a parallel hybrid vehicle actually. So you can find, and one can make series and, parallel hybrid. And even one can think about this kind of architecture like complex and all, where you can see that rear wheels is driven by the motor and front wheels also we have engine and motor also. So both systems are interconnected again here. So using a battery and then inverter. So this kind of complex kind of reconfiguration actually you can do some configuration whichever you wanted to, make it possible based on your application driving cycle, you can make it on actually. That is also possible. And to understand this, what is a power flow in series hybrid? Let us, you can see that battery drive. So now this is engine, and in this case, battery driven means, engine should be off condition, battery, powertrain, and then motor, transmission, and then finally connected to wheel. So this is what the, power flow will be, where engine will be off condition, where you can see the battery recharging. That means, battery recharge, engine will drive your vehicle. At the same time, engine power also can given to battery for charging. This is also possible. And then hybrid, so that means both engine and battery should be able to give the power to the vehicle. So maybe some cases, where they require more than rated power, like hill climbing or something. So in that case, you need to depend on the hybrid version actually. And regenerative braking means, so you have this, yeah. So you have this, vehicle kinetic energy will become, finally it will come to battery actually. So in that case, engine will be off condition. And next is the parallel hybrid. In this also you can see that power restraint, that means both engine and battery will drive your vehicle. Regenerative braking, that means engine will be off condition. So your vehicle kinetic energy finally will connect to the battery, okay, by chemical. And then, battery recharging, that means engine will drive your vehicle. Engine power also will be supplied to battery. Zero emissions, that means engine will be off condition, battery power will be given to vehicle. And then conventional vehicle, that means engine, battery will be off condition, engine will be driving your vehicle. So this is what the power conversions will be there. And similarly, you can go with a combined hybrid also. And then we have we have some kind of targets also given by recent, many recent calls by government. Also industry also. So typical one thing, basic, standard, like, so if you are designing with, power electronic controller for EV, and then you should have a 95% efficiency. If it is combined efficiency, the motor and controller, it should be more than 90% minimum. So that should get it actually. Ideally, so the electric traction motor also, so you should have this kind of characteristic: high efficiency over a wide range of speed, especially with regenerative braking, and then high torque and high power density, high torque and low speeds and starting and acceleration, hill climbing, high power at high speeds for cruising, and wide constant speed range. This is very special and important, that in our CPSR. And then fast dynamic response, and then we should operate in dynamic conditions as frequent and stop, and maintenance, overload capacity, robustness, low noise and cost. So that means, these are very important characteristics one has to maintain through your power electronic drive. So that is the reason actually now we are discussing this wideband devices are very much important to drive this kind of, ideally you should get this characteristic. Using conventional power electronics, maybe we have a lot of challenges. To overcome those challenges, now we are bringing this, wideband gap devices for this, getting this kind of ideal characteristic for electric motor for EV application. And then you can look at the, evaluation of, different EV drives actually based on DC, induction and up. So you can see that induction motor is still in the race actually. It's a very much competitive for a conventional, a PMSM and PMBLDC. And still, it's technology is not mature stage for the specific reluctance actually. But most of the now industries are going with permanent magnet based actually, because efficiency is more when compared to that, and maintenance also, we don't have much maintenance also. So, but still, it's not, they are not going, earlier started with induction machine. Now people are mostly going with permanent magnet. This is what the layout actually, you can see that, this is what you can see that complete, some kind of schematic block diagram. You can see that battery pack, and then, so BMS will be there, and then DC converter, inverter, motor and all. We have auxiliary systems, and then controller for inverter and all. And charging also, there are levels: level 1, level 2, level 3, and most of you are aware of it actually. It depends on AC system. So India, we have, 230 or 240 voltage will be there, and then it's a limitation actually. One has to see that sometimes we listen that, so 3.3 charger. So if you go to shop, and if you go to, two-wheeler or four-wheeler to buy it, they will tell you this is my car rating. Suppose let us go to Tata showroom, then, they give the, 3.3 charger for this, Tata Tiago. So then, if the battery is, 20 kilowatt actually, 20 kilowatt hour. Then if you want to get a full charging, you need to charge for 6 hours minimum or 7 hours actually. That means it is a limitation of the whatever power supply that you draw from the, where you connect for charging. Because in our homes, so you have a 6 ampere socket will be there, and then you have a 16 ampere socket only. So beyond that, we don't find any sockets actually. That is what maximum power we have limitation to draw from the home actually. Similarly, If you want to go with more power, then definitely you need to go outside the charging, go out of, and then charging station. Then in that charging station, they will draw the power from the transformer from the utility company. Is it right? Then there will be a chance of going with fast charging and application where we will convert this AC to DC, and then we will give it to vehicle. So okay, so this is what off-board chargers also into the place for the fast charging application. Of course, one can depend on DC fast charging. That's what nothing but AC to DC conversion will happen. It's off-board charging. And inductive charging is very interesting. Actually, two types: static and dynamic. Actually, where you can park the vehicle and then get the charging with a 1 feet distance minimum, and then we can transmit the power from primary coil to secondary coil. I think to design that, as a previous section was very much useful. You can use, you can simulate that kind of wireless charging system using the LTspice simulation also. So many of my students also execute. And another way is dynamic, where we can try to run the vehicle on the ride itself. You can try to get the charging also. There are some case studies also developed in USA. And you can see the South Korea also, they successfully implemented for wireless power transfer for heavy duty buses, heavy duty vehicles, like particularly for trucks and all. So we should have some intelligent infrastructure definitely for to maintain and have this proper energy management with them. Otherwise, the smart grid, definitely we need to take the smart grid help actually. Is it right? So we need to know where the charging stations are available, and then what is the queue number, whether they get the charging there. So a lot of another, interlinked with the user and then vehicle, it's very much information is required. So, okay. And we can see that, right now we are part of this EV30 at the rate of 30 campaign. So there is a simple target is given to us. 30% of the market shares are electric vehicle in total of the all vehicle except two-wheelers by 2030. So India also is aiming for this. And right now the operating cost is, very much high for the conventional vehicle, but operating cost, very less. Already compared 5 rupees or 6 rupees will come down to 1 rupee or 1.5 rupee for four-wheeler. Okay. And now we can see the fuel cost for a conventional fuel, it's very much high. Electricity price is less. And right now one drawback is the electric vehicle. So battery cost is high. So suppose you are aiming for the 10 lakhs rupees or vehicle, then definitely battery cost will be 40% minimum is there in the market. 40 to 50%. Minimum is 40% actually. So now slowly, the battery cost may also anticipating that it will come down. So because of a new invention, the battery technologies, beyond the lithium ion, like lithium sodium batteries or lithium sulfur batteries actually. So maybe we are going to come up with a new battery systems actually. Let us hope that battery price also will come down in the future. And projections are also good. And then slowly you can see the declinement in the conventional vehicle. And it was exactly started in 2009 around actually. And many companies started slowly releasing their model. And OEM companies, original equipment manufacturing companies also, they announced this much. This is the year we launched this much segment of electric vehicles into the market. And we have a target, these two targets: 30% electric cars by 2030 and 100% battery driven buses in the urban cities by 2030. These are the two targets. And surprisingly, there are some companies, they already announced the ban on IC engine production. Even India also, one of the statement they said, one ministry, that 2047, by celebrating of the 100 Independence Day, we may also ban the IC engine production in the country also. So there was already announcement for the thermal power plants also, similarly electric vehicle also. And it was started in 2012 by, establishing this National Electric Mobility Mission, NEMPP. NEMPP 2020, we have targets, and we could not achieve much all the target, but it was a good start from 2012 onward. And then later government was started in 2015. This is a fast FAME scheme. So fast adoption manufacturing and the hybrid electric vehicles. And we completed in first phase. We are in second phase also. We completed this 2024 July actually, June. And then Niti Aayog also timely on they also monitor this in development in EV, and then they have also supported with a lot of reports and strategies and with a lot of committees also. Tata Motors, they won the first public procurement EV tender. They established with the help of energy efficiency service. This is a company, joint venture company of Government of India, is responsible to take care of the EV charger stations in India. And this is a website, we can have a lot of details actually. If you want to know about what is the models and who are the OEMs, dealers for the electric vehicle. So FAME website is there. You can just search in Google, and then it comes under Department of Heavy Industry. Okay. And FAME scheme phase 1, we have sold close to 3 lakhs, 2 lakhs 80,000 vehicles, or we have sold it actually. And FAME 2, actually, we have close to 6 lakh, vehicles are sold actually till 2024 June. So totally put together from 2015 to 2024, we have sold 10 lakhs, vehicles we have sold in the electric vehicle segment actually. And if you want to purchase any vehicle, two-wheeler, three-wheeler, four-wheeler, if you want to see that whether it is authenticated, whether it is approved by government, whether we can get the incentive, then you can go to this website and see that that model is presenting or not. So if the model is presented, and then if you are able, then you can buy the vehicle. So otherwise, what will happen is nowadays many particularly two-wheeler companies, many imported and white label companies has come. They are not original manufacturers actually, frankly telling, and they're importing a lot of things, and then they put the label, and then they try to sell the vehicle. But after some days, actually the company also they're closing down because of their own startup problems and that. So before buying that anything, one has to see this website and see that whether your model or the company is listed here or not. Then only you should purchase the EV vehicle. This is my personal suggestion. And then uh, so we have very good information. Website is there. This is only one website maintaining Niti Aayog for electric vehicles, CMRIT actually. So you will get all full details about these electric vehicle developments, what happening in India, a lot of tools and charging maps, tools, calculations, everything, resources, material, and what are the standards we follow. Everything is one shot, one platform. This is a website we need to follow actually. So this is maintaining Niti. And this is a ESL, I already told, this is the company that is responsible to getting the EV infrastructure in the country. And we have a lot of hybrid vehicles launched in India. So these are luxury models are available actually, Toyota Prius, Honda Accord, Army, MG Hector, and hybrid. So as per my remembrance, actually the Maruti Ciaz vehicle was the first vehicle launched in India in hybrid mode, and later a lot of vehicles, Swift, Ertiga is there, Baleno, Vitara, many are there. And this is a Lexus model. And coming to electric vehicle model, Mahindra E20, this was the first model. And prior to that, there was one Reva model from Bangalore-based company. There was electric vehicle, I think, long back actually. And then a Mahindra E2 and Tigger was the vehicle. And then after that, Tata Nexon EV, and then Hyundai Kona electric, MD ZS EV vehicle. These were up to MG ZS, up to before Corona, it was there. After that, there was a gap and almost 2 years, and then we have struggled. Automobile companies also they struggled, and finally again Tata was launched in Tata Tiago after the pandemic, and then Mahindra SCV 400 EV, and then Comet EV recently last year, and Tata Punch also last year it was launched. So these are very successful models in the market actually. And then the charging infrastructure, we primarily focus on metropolitan city and other places also. And this was one development, like 2020, India's first public EV charging plaza. It was inaugurated in New Delhi, and four plus slots were available. And then they charge 10 rupees per this thing, and then running cost is just 1 rupee 25 paise, 1 rupee 50 paise. This is a charging station established by Government of India, ESL, so Energy Efficient Service. And we have maps like this you will get nowadays actually, and we will see the lot of parking places like this, private companies and metro stations, and these arrangements are getting now arranging many places in the country. And success of EV charging depends on three parameters: accessibility, utilization, and cost. And then government, they promised also, they said many places, and they sanctioned EV charges and all. So like this, and FAMES too, they sanctioned 2,636, but those are not installed. All in all the states actually. Still, it's in progress actually. And we have a roadmap from even from generic from International Energy Agency also. We need to get by 2050 50% of the vehicles, so light duty vehicles sales should be there worldwide. And IEEE also contributing from their vehicular technology society, and IEEE transportation electrification community also. And one problem statement for all of us actually, impact of the electric vehicles on peak demand. So this is very much interesting, and many researchers also they are doing a lot of their PhD work also. And we already address many other sectors, like for example, you take the agriculture sector. In agriculture sector, to avoid this peak demand, then government has made separate lines, transformers, and they dedicate some of the hours, so 6 hours, 9 hours, and all. So like that, they kind of even they tell the farmers to keep their capacitors for reactive power, don't run the reactive power from the grid. So this kind of arrangement they did, they arranged to avoid the peak demand in the system. And similarly, so electric vehicles also one has to, come up with, government and utility companies will come up with a strategy. How do you, schedule the electric vehicles if you are, if you're having if you're having them in the large scale? Okay. So this kind of problem states are very much interesting. And next is even optimal placement of the EV chargers and, PM and those things also very much interest to us. And IEEE Smart Grid initiatives also, this wireless power transfer and electric vehicles has taken priority, and with the power electronics also. And private parties like this, you'll find them many, including Tata Power, many other. You'll find the maps and all. You can put the location and then city also. So you'll get a map where your charging stations are available, including government and private. You will get a map like the Hyderabad, for example, like this. And India, what aiming is, the Indian government ESL, they are trying to set up that, kind of, on highways every 25 kilometers and both side one charging station. And at the same time, 3 kilometers by 3 kilometer radius, at least, one charging station should be established in the country. So these are targets they maintained actually now. So hopefully that will get in future years and all. And this is one projection of cost of the electric vehicle charging station established. Yes, definitely we need to see that charging connection from the utility. So you need to take from utility permission, all these things. And startups also, many startups are coming up. India's largest one are coming, starting this one. And this is what the service-based startups also coming into EV sector actually. And we have regulations also from the government of India. So public charging and infrastructure, what is the voltage, output voltage we need to maintain, what kind of suitable for which kind, power range. Okay, so we have fast charging up to minimum. This is combined charging CCS 50 minimum, and Chamode is also minimum another 50. But voltage levels, it's given differently actually. It's meant for four-wheeler vehicle. And another slow models is called as a Bharata DC and AC. So this is what the voltages we need to maintain as output of the, so these converters actually. And Niti Ayog also given the specification of battery. So in case of battery, two-wheeler 1.2 to 3.3, but nowadays you can see that even some of the companies like Ola, so they already come up with more than 4 kilowatt, 4 kilowatt hour battery also. So these kind of battery specifications also is going amended and based on the technology development from the industry. So this is how it will go actually. Okay. And one can see that this chargers also now EV electric vehicle supply equipment also now it's getting trending now, and the different technologies like where you can have AC and DC and then outboard and onboard chargers also. And the EV we can see less than 7 kilowatt, we can have both options are there, current AC and DC we can depend on. So 7 to 22 kilowatt we can see, and if at all you want to go with beyond the 22, and definitely it's high power charging, and it's depends on a DC fast charging technology only through power electron. AC to DC conversion will happen it. And this is what we can see that maybe this is called EVSV, electric vehicle supply equipment. Inside there is no conversion of AC to DC, that you should understand. So the conversion of AC to DC will happen inside the vehicle. That means your charger onboard charger. So this is only like a stabilizer kind of thing actually. Nothing will be there, no power conversion AC to DC. And similarly this also, and one can think innovative ideas like where this current pole itself we can use that a facility to convert them a EV charging station, okay, for the two-wheeler application. These are innovative ideas for some of the startups also, they coming well. And this is some of the drawings actually where you can depend on solar and then get the charging, or you can depend on the utility company from transformer and get the charging for vehicle, or in at home you have energy meter, from there straight away you can tap your energy and then getting to car or bike for charging and all. And when you depend on this grid or solar, definitely we have net metering system is there. And battery swapping technology is another technology where Indian companies also, government company, public sector companies also, they are into now this business now. So we have both advantages and disadvantages. Okay, barriers are there. So we need to overcome the barriers, because when anybody come for replacement, so they'll keep the aging battery and then they may take new battery, and also they should be kind of mapping also. To say that same model, okay, same rating, that we should be also capable. There are some of the barriers also there. So authentication, all these things are issues when you develop this kind of technologies into the market. And we have good projections actually from Niti Ayog also. A lot of EVs we are projecting from 2030. So that's the reason we have a good market in India also. And every state, so they have their own EV tariff that is charged from vendor. Actually, I mean that electric vehicle, a charging station owner. So in case of Andhra 6.7 and Chhattisgarh 5 rupees only, Maharashtra 4 rupees only, like that, and like Tamil Nadu 5 rupees to 8 rupees, they kept it actually. So on the after that, actually a user, I mean the vendor, the EV charging station, he will charge more than this from the user actually. Suppose in Tamil Nadu, if they say government is collecting 5 rupees, then the EV charging vendor, okay, station owner, he will collect 15 rupees to 20 rupees per you from the user, because some amount will be profit and some other he will be payback period. So some amount will be maintenance of this EV charging station. This is how they will charge the amount actually from the user. And one thing, as I already discussed, EV battery. So that is getting cost actually right now. So we need to see that how this will come down in the near future actually. Right now, 40% of the cars, EV vehicle comes from the battery only. And right now there is no restrictions. Anybody can start the EV charging station, very simple regulation. Okay. And future, but a lot of complicated, regulations may come actually. Right now, any individual can establish a company and then they start the EV charging station. Just make a agreement between the, this thing, land holding agency and then yourself, and then to connect to the utility company and get the connection, transformer connection, and take a land or buy it, or you can take the lease and then establish the EV charging station. Simple, very simple, actually, no regulations actually. And coming to standards, actually, we follow IEC. For we follow IEC standard. Those IEC standard we adopted and we convert them as a named as a BS, Bureau of Indian Standards actually. So this is what EV standards are not is there for every power range actually. It's we adopted them actually very well. So now we have a communication protocol is the Canvas, PLC, and EV charging, and connectors and all. So these were the original standard. So IEC 614851 and general requirements EV connecting charging. The second one 21/2, and this is the requirements for AC DC converter and EMC issues on board, offboard charges actually. And another one is this is a connectors, plugs and sockets and units. So anybody wish to start any startup and they want to work in EV, and definitely we need to comply with this IEC standard. Otherwise you will not get a certificate to launch your product in the market. So that's why the reason all the industry they need to 100% comply with the IEC standards. Okay. And we have SAE standards also in related to communication also. So this is also very good standard actually. And then we adapt them into IEC standard is actually now we are following that actually very well. And you see some of the drawings are given in standards, like for example, fast DC charging. Now you take the power supply from the AC and you have usually the primary rectification with power factor correction is a default inbuilt, and then you will get a non-regulated DC that will be converted to AC to inverter. Again, use the isolation transformer and then secondary rectification you do, and then you will get a regulated DC and then connect to battery. So look at this, every this part total this part is outside the vehicle. That means it is a offboard charger. Only battery is inside the vehicle. Okay. And next is you can see this is a layout now. So this primary rectification only, this is outside the vehicle. That means this is only DC fast charging again. So now this is outside, but inside the vehicle there is onboard. You have onboard charge. The conversion will happen AC to DC outside, but this electric charger onboard charger is inside the vehicle. So inside the vehicle. So this is a change you can have. So another is this is also instead of doing this isolation next stage, you can do isolation in the primary side initial stage itself, and then do the secondary purification, and then finally regulate the DC using DC regulator connected to battery. So this is how you can see again here also battery is inside the vehicle. And one can depending on only DC sources like solar, any other you have a DC bank, then you can use directly DC instead of getting AC and then convert it into a DC. You can eliminate that and depend on it. And this also you can do the possible. So here also this conversion whatever regulation is outside the vehicle actually. And we have communication standard. There's SAJ 28471. Actually, is very good standard. We need to follow for communication. Actually, without communication, one cannot build the EVSV systems or EV chargers. And cables also based on the your EVSV outlets. We need to connect with the proper cables and all. Okay. And these are full standards. Also SA from SAE, from China standards also there, Bureau of Indian Standard, and battery packs also we have standard. That means, if you have a standards, that means technology is already proven and it's matured, then they convert into standard. And you can see that the wireless power transfer also standards are there. So which means, the technology is already, validated. Okay, it's proven. They made into and standards. Now one has to now implement that. Simple, actually. So that way we should go ahead. And what are the workflows with EVs? What are the possible? One is EV charging stations, actually. So where you have level 1, level 2 charges. In India, we go with level 2 charging, actually, based on the input voltage. So now we can see that EVSV will be outside the vehicle, and then so this onboard charger will be inside the vehicle. And now look at the level 3 charging. So this EVSV plus the conversion AC to DC will happen outside the vehicle. And then of course you'll have a onboard charger also inside the vehicle connected to the battery. So from here, what we do is we can connect it to even AC also, DC also. This kind of possibility is there for electric vehicle. Level 3. So now another technology is getting ready, that vehicle to grid also. That means sometimes there is a question, why vehicle power should be sent back to the grid? Okay, so maybe for an individual case may not be that much kind of worthy, but whenever we have dynamic pricing in the system, right now we have static pricing in the electricity. So when you have dynamic pricing, then if you have large number of vehicles, then if you don't use them in the kind of maybe night time or something, then you can send back power to the grid and then you can earn money. And morning maybe you can also charge your vehicle with a low rate. Okay, due to dynamic pricing. So these are in some of the studies also in your European countries, they made a case study that the drivers also earning money. So through this V2G technology. Beyond V2D, there is a V2X, V2B also. Like your vehicle battery can also behave like, can work as a home EPS battery systems, actually. So instead of depending on your battery, lead acid battery and all, let us use your lithium ion battery of vehicle only to supply the emergency power for your home, or similar any other application. So maybe function halls or something. That way, V2X also vehicle to anything. So that is a technology also. Now people are experimenting, and then many case studies, pilot projects also implemented, actually. And this was the one of the case study in Europe. I was telling that. So even this in Japan also in 2011 there was a earthquake. So Nissan Leaf one model is there, EV vehicle. There are 66 vehicles that are used to stabilize the grid. So that means there was a blackout in the that place. So total blackout. There is no source to generate the power. Then EV vehicles now it become a emergency source of power supply to restore this power system back to the original condition. So these are the ways many case studies also will tell us. And this is what the EV charging station, level 1 and level 2. Okay. And yeah, previous picture, it's similar to, what I showed, it's a larger view. And you can see up to, this is, we'll go based on 16 amperes, and this thing we can go 1.92 kilowatt, and then we can go 15 amperes, 16 amperes, that is Indian condition level 2, and up to 20 kilowatt, 22 kilowatt maximum we go. And level 3, you will go with, DC fast charging, actually. So buses, we go up to 250 kilowatt also. And we have, IEC standards we follow, and then connectors also based on that. So level 1, level 2, we have SAJ 17772. And if you are level 3 charging, then we will go combine, CCS mode charges connectors we use there. And this is what EV SE. So electric vehicle supply equipment. So in that, if you see the box, actually, so inside the box, you will follow this kind of diagram only. So we take the single phase supply, we have current sensor, voltage sensor, and then that will be going to measurement box, and finally it will connected to microcontroller. So now we have here, so we have a relays are there. When you want to connect this supply to the vehicle, so this relays will be operating. And here we will connect one circuit, like a pilot signal generator circuit, actually. We will generate the PWM pulse with 12 volts, 9 volts, 6 volts, and then negative voltages. So based on that, that is also as per the IEC standard only. So now based on that, whether your connector is connected to properly to the vehicle or not. So based on that signal generator PWM pulse only, then this relays will be operated, and this charging will be enabled from supply to our vehicle. So now we have other auxiliary systems also required. Power supply will step down, and then finally user wants some kind of communication. We use wireless communication. Okay, and then user also we require some kind of interface smartly, like a touch screen. Maybe your human interface system, a display system is required. So this kind of arrangement we see in EV SV actually, and similarly for DC charging also. So this is the thing. Nothing. I mean, AC to DC conversion will not happen that EV SV actually. Okay, in case of two-wheeler particularly and four-wheeler also, except this fast charging. And this fast charging you can see. So AC to DC will happen, and then DC to DC also, and then it will connect it to vehicle. So we have CAN bus communication will be there, vehicle between vehicle to power electronics. And now one can think about hybrid energy storage systems also, battery and then ultra capacitor. Sometimes we need to have surge power, and where you can get the power from ultra capacitor and then connect it to inverter and then motor. And we can have this kind of arrangement. So in this case, both voltages are same. Wherever the battery and ultra capacitor is different, then you need to bring the DC converter here. And this U diode and unidirectional power flow, you can connect them, and you can see the ultra capacitor battery placements are reversed, and then these both are in parallel connection. These are reconfiguration, whichever you wanted to make them use, and then you can connect them like this and that. So as I mentioned just now, so one is you will get a charging from the grid to vehicle. That's what conventional charging, and vehicle to grid, and then now people are now working on this vehicle to home, vehicle to building, or vehicle to anything. So this thing. And this is a smart charging system, okay, architecture. So let us assume that you have many charging stations, maybe within the city, 4 are there. Then you need to link with this smart charging management system that is connected to utility company, and finally you draw from the ultimately you draw from the grid only. So how kind of smart interconnection, not only power, communication also has to be established between the charging station. Otherwise, we cannot support the users actually. Okay. And right now we depend on this open charge point protocol. Even one can students also, they can build the projects using maybe for example like Amazon AWS and so you can write a Python code and then see that how kind of EV between the linkage between EV AC and the vehicle also. So this kind of thing and all we can do that. So right now this protocol is open source. One can think about hybrid, all these things. So V2X, these are very popular companies. They work on V2G vehicle, V2X and all. So government does, we have a lot of employment opportunities. And this is one case study where you can see, assume that, so PV and then, PV, which is unidirectional power flow, battery bidirectional power flow, and then power grid. So we have, let us assume that there are 5 vehicles has come into picture. Okay. So we have charge controllers also there. So let us do some energy management. Is it right? So grid voltage, maybe power will not be available all the time. And then battery is depends on charging, and solar also definitely morning to evening. Then you need to work on this energy management. So vehicle has come. Okay. So then you need to see that what kind of strategy you need to build it. So what is the power available with the EV, and whether what way, getting power from the EV is cheaper, PV is cheaper, or grid is cheaper, or battery is cheaper. You need to see that. And the people are coming with a different, not same model, different models, different charging levels they come with. So what kind of, algorithm that we build it. And in that also one can build in a fast mode, slow mode, charger mode. Even somebody like, they will start with charging mode. After the 50% charge, they wanted to get into slow mode. Fast mode, they will charge more money. Slow mode, they'll charge, less money, because you need to wait for more hours actually. So this is kind of, algorithm one can build it actually, and then getting implemented for EV charging stations actually. So now we can see new vehicle arrive, and then let us select the mode. Okay, and then based on that you can see, and finally it will take the departure. And in middle also you can shift it to other mode also. And IoT is getting now developing stage for the this to support this EV infrastructure actually. So this is one thing, it's very good. And blockchain technology also. So when you have the multiple charging systems, as I mentioned previously, so this blockchain technology is also getting implemented in this EV smart charging infrastructure. And future also we can think about this very good developments like a P2P energy trading. Okay, so you have aggregator. Okay, community is there, one community, this is another community. So there are people like a presumer. So he has a solar panel, he will consume the power as well as for home needs, as well as he will deliver the power back to the grid. So like instead of consumer, he will become a presumer actually. So now any peer can be connected to any other peer. So this kind of trading. So like even like in future you can see that in home to home trading. So myself and then my neighbor, so we'll exchange the power. Okay, so this is kind of an energy trading will be happening. And it can be extended for the blockchain level also. This research is going to be happen actually in India also. So one is cyber physical system is another good area for any engineering systems and all. So electrical engineering particularly is getting advantage actually, because in electrical engineering cyber physical system, all our devices equipment physical, like transformers, motors, generators, circuit breakers, relays and all. So now we can model them physically, and then connect it to cyber. It's very easy. So electric vehicle also, now here the electric vehicle charging and discharging, it depends on this model is social layer, and then physical layer, that is aggregator, where he is able to connect with the control center for the charge. So this way cyber physical systems also can be built for electric vehicle application to make proper energy management also. So in that we can bring the social behavior also. So that is what the future electrical power, how electrical engineering go ahead actually. So there are some case studies I am referring that. So now look at the future opportunities, challenges in EV sector. One is specially designed electric motors. This is one thing, because now we are importing technologies from mostly from China. We should avoid that actually. So multi-level inverters, topology, control algorithm, one can build. Many people, they will come with new topologies, control algorithm, and parallel inverters and redundant, because reliability is very much important. So in this lecture also, I'm going to discuss about in future slide. So reliability issues and all. And hybrid source and energy management. That means more than one battery. So with battery and fuel cell, and battery in conventional vehicle, and then do energy management. The next generation batteries, BMS, and EV infrastructure in that static, dynamic, wireless, and then renewable energy based charging stations, and then vehicle to grid, vehicle to X, and integration with the distribution generation microgrids, including optimization and demand response and transactive energy. Because ultimately, any deal with any energy system, it depends on economics only. Is it right? So we need to see that what is investment, expenditure, and then payback period. What is the cost of energy and all. So that is what now we can address in this problem actually in this area. So smart charging infrastructure, and then cyber physical system based solution. So right now we have this directions are there for us actually based on the literature now, and progress in the industry, in particularly EV sector. And people are coming with a lot of AI based application in EV also. So wireless power transfer in EV, and then AI in energy management, AI in system architecture, AI in electric vehicle design, and AI in power supply management, AI in softwares, okay, and life cycle management assessment. So like this, we have even implement planning and EV charging infrastructure, particularly charging stations. So like this, AI applications also plenty of opportunities are there for EV sector actually. And coming to power electronics, popular trending. So what kind of features we can execute through power electronics? Okay, and one is people what can always we have a scope power quality. Power quality we need to improve that actually. So there's always we have that in that power quality. So with devices, without devices, with devices means it's not cost effective. We are making additional cost. Is it right? So now people are coming with a lot of new methods like multi-bus, multi-stage, multi-level isolation transformer, solid state transformer like that and complexity reduction. Always we have a scope to come with a less number of switches so that they can reduce the losses, and then we can reduce the size of the converters also. Efficiency losses we can, we can concentrate, and then we can get the more reliability and stability. And then multi-port and multi-converter, like a multiple input, multiple output. That is also advantage. And hybrid and parallel operation and dynamic conditions analysis. The emerging semiconductors, silicon carbide, gallium. This workshop, your FDP is more focused on this, silicon carbide and gallium nitride switches, and novel algorithms for hybrid algorithms. Maybe we can sometimes we can apply this, this conventional algorithm with with advanced algorithm like ML and DL. So that is also possible. So another is now in the market is these things are getting ready. So beyond that, these developing semiconductor, smart power modules. That means your power electronics, okay, whatever that is, a MOSFET or IGBT or SiC or GalNAND. So those can be easily connected to cyber. So okay, with IoT. So that is also now is going to be in future. We are going to be trend how the power electronic switches can be connected to communication channels. So this is also very much interesting for us actually. And beyond electric vehicles, these are the vehicles we are going to see in the future as a witness actually. So hydrogen vehicle, solar vehicle, all electric aircraft, fuel cost, flying cost will come down drastically. And there is one case study also there successfully in 2022. Autonomous cars, many many companies, they made a successful trials in autonomous virtual cars for patrolling other security purpose application. And then flying cars. There are two popular companies also, they are selling the flying cars already. Research is being already done. There are two companies already commercialized these flying cars also. And coming to power electronics role, yes, we do have a lot of importance in power electronics actually. So one is motor drive control. Is it right? Because already mentioned that the motor should be drive with properly with the ideal characteristics. So that is only possible to power electronics. Is it right? The combination of motor and power electronics that we call it generally so motor drive. So to get ideal characteristics for speed and torque, is it right for a motor? And then BMS. So to implement BMS, yes, we need to depend on this power electronics actually, and particularly the charge converters, the DC-DC converters actually. And then there's onboard charges and fast charging implementation. Definitely, we need to depend on this power electronics. Of course, off board also. And regenerative braking. Regenerative braking, this power electronics will play a crucial role. Otherwise, we cannot tap from power from the mission. So which will act at that time, generator, that power will be stored finally into battery through power electronics. Is it right? So now, what are the advantages? Okay, if you depend on more on power electronics. Actually, this power electronics is absent in the conventional vehicle. That you should remember. So now, if you place the drive your vehicle, okay. So using power electronics, then energy efficiency, we can minimize losses and all this thing, and we can also make it compact and less weight design. Because if you instead of power electronics, if I use some kind of transformer, is it right? So that is also sometimes alternative solution for maybe getting some kind of particular voltage or something. So then that's not a viable solution for design, because more weight will be there. So it's not a compact solution. And if you want to have high speed and crucial control, precise control, definitely the power electronics through switching only it's happen actually. Otherwise, it's not direct supply. We cannot control it. Is it right? We know the advantage, like even a small experiment. If you do that in an induction motor driven by direct line supply, and the induction motor driven by the drive. So there is a lot of ideal characteristics or desired characteristics that you will get only through drive only. And of course, we can integrate the renewable, yes, a vehicle to grid or any solar to, battery charging. And now we can see the advancements in wide band, band gap, semiconductor device, silicon carbide, gallium nitride for higher efficiency, fast charging. And we have limitations. That's why we are going to talk about silicon carbide, gallium nitride. So in case of conventional silicon, power devices, like, so they have, a lower band gap. Okay. I think these are the, points were discussed previously. I hope actually these are general topics. Okay, let me cover it. So now we have also other disadvantage, limitation is high on resistance, because of that we will get power losses will be there, power dissipation will be high, and switching losses, particularly switching losses is another major challenge always when you deal with silicon based devices like MOSFET and IGBT. And then size constraints also there, and then it will have we cannot achieve this breakdown voltage as much as high. That's it has a limitation now. That is also another point. And temperature limitations also is a very much problem with silicon carbide. General silicon power devices. And that's why we are going with a silicon carbide device. Okay, so it will have a higher breakdown voltage, lower resistance, and then better the environmental performance will be there when compared to silicon devices. Similarly, gallium nitride also, it will operate high switching speeds. Is it right? Then we can use these kind of devices in the kind of EV chargers and all, gallium nitride based, because high frequency applications also plenty of there for gallium nitride. And we can see that the properties, you can see particularly large band gap. Actually for gallium nitride, you can see silicon carbide, it's almost 3 times, actually 3 times electron volt band gap. You will find them with these devices, WBG. And then it will exhibit this in a higher breakdown voltage, and also better thermal conductivity, more than 3 times you'll get it. Fast switching speed also it's possible. And finally, you will achieve higher speed, and then higher efficiency, greater thermal conductivity, and less weight it will come down. It's not many other applications there. Ending we can see that using carbide we can go with more than we can touch 10 megawatt. Okay, and even we can see that this kind of application you can see that even in the future also solar large power plants and something like. Okay, and we can see the voltage raising also we can go up to even right now 7.5 kV actually, but right now very popularly what we use up to we go 1.2 kV 1200, but there is a possibility still we have that kind of switches also in the market nowadays. And we do have a lot of challenges in the conventional vehicle powertrain. So power efficiency related, thermal related, size, reliability, high cost, and all these things, vehicle degree. So now we are going with wide gap devices actually. So because of advantages, okay. So high voltage, high power applications where we go silicon carbide devices, inverters and motor drives. This one. Whereas gallium nitride is highly preferable for the these onboard chargers and DC converters in electric vehicle application, because we require high frequency application we implement there. So that is the reason actually. So now we then anyway we'll achieve this all higher efficiency, thermal connectivity, good temperature condition and all these things. And now, as I mentioned just now, SiC-based inverters and motor drives, it's available. Many architectures available is 1.2 kV actually. So now we are going with higher efficiency, reduced thermal, and gallium nitride is prepared for onboard charges and DC, and we'll get fast charging is possible gallium nitride actually. And this is what the this thing, okay, and that applications I mean. And coming to reliability concerns, actually, reliability concerns, yes, we do have concerns with this, wide band gap devices also. So what are they? So one is, gate oxide degradation will happen. So what will happen is, when the charge trap is, when they well, then it will cause the threshold voltage instability also. That is also another problem. And dielectric background, because already we see that, it's a high dielectric, it is possible with the wide band. So that kind of sometimes it will that was damage then permanent failure. That means we need to replace the another device. There is no other alternative to repair or something. Okay, that's the thing, another problem. And then thermal issues and packing reliability. So because when they make the manufacturing place, so when they wanted to make this less compact, in terms of space, so due to mechanical stress, these more thermal reactions will happen that will cause it to, reduce the durability also. And of course, EMI issues, because we are depending on high speed switching. So high speed switching, when you do, definitely, noise and interference will happen with the other communication systems when you have nearby in the vehicle or something. That's also another problem. And short circuit weakness is there. Okay. And then, material defects also, because from the manufacturing side. So this is kind of, some kind of limitations also there, which will affect seriously reliability. Now, industry also working towards this actually, how to overcome this reliability concern, particularly this wideband also. And this is one of the kind of solutions from the literature I'm projecting here. And one is, switching losses. Okay, switching losses. The issue is, switching losses actually, it is going to, due to this fast switching, electromagnetic issues will be there. High, dV by dt will happen. Overshoots and voltage rises and all. So what will happen? This cause will, transitions will happen. Is it right? Then to mitigate, what is the solution? We need to optimize the gate driver circuits, okay, with proper gate resistance selection, so that we can limit that speed. Actually, we can reduce the EMI also, and at the same time we can depend on the soft switching techniques like a ZVS and a ZCS also. Then we can minimize the losses. These are some we have issue. We know the causes, but we have solution from the past experience with other switches. We can also try here how to mitigate those losses and all. Okay. And next is other reliability concern is voltage spikes and voltage, over voltage tests actually. When you do this high frequency switching, and then, this will obviously it will cause that actually. So, and then for which to limit that, next is, parasitic inductance also will vary in this, and then that will cause unwanted, voltage spikes also during fast switching. Then it will impact the voltage stress and failure, and increase losses also. But we have a solution. What is the solution? Stumper circuit. So it's very simple, very popular. What we know is stumper circuit. We can use them, and then mitigate the voltage spikes and control the voltage levels. And what is it, the dV by dt actually across the switch. So that is also that is possible. And then active gate control that we can use, and optimize PCB layout, because we are talking about how the kind of kind of inductance that we try to minimize that is only possible to design
how even though industries are trying to make a compact and less weight and then everything in a small box, I mean small PCB, because there we need to focus on optimization also and then packing issues also. Okay, without any mechanical stress on the switches and then complete board actually. And third one is material robustness and degradation. And here SiC based in this gate oxide degradation is there, threshold voltage instability. Whereas material wise gallium-nitride issue is voltage collapse and current collapse and then trapping issues will be there. And but we have the issue, we have solutions are possible. One is in the manufacturing stage itself, we need to find out what is the defect and how it will cause. And people will do, industry will do a lot of simulation environment. And then the testing also they do with the different dynamic condition. That's one thing. And thermal management is one where we need to provide the cooling techniques. Okay, how to maintain the good thermal management using better cooling techniques and all. So these were the solutions also possible. Okay, this is the third one. And now feature trends, okay, in this area actually. One is high power, high voltage power trains actually. So now right now we are industry, we have 1.2 kV, but beyond that also high voltage is also possible. And many other applications also where we can focus high application, high voltage. And then AI driven power management, where predictive model, predictive algorithms and machine learning based and real time diagnosis for reliability and system efficiency, how can improve that actually. This is one of the, so that means uh, we can adopt this AI based real time diagnosis for this finding the limitations of wideband. That's one thing. And third one is one good interesting, the cooling techniques or advanced packing system for 3D integration chip scale, so that it will come down, even with a better optimized PCB layout for the this wideband devices and all. In cost reduction, okay, and definitely mass adoption strategies, also scalability in the manufacturing and all. And this is the future of the WBG semiconductors. Okay, powertrains definitely we'll get a higher efficiency, compact dividends, and even weight also will come down actually. Okay, and we'll get a fast charging also. It's possible. And long-term performance durability is a critical issue that we need to address through reliability concern. Okay, that's one. And of course, we have a lot of scope is there in materials. One means AI-based research and this thing. How do you connect with the cyber and all? And this is what one of the some of the example I'm presenting here. So this is one Texas Instruments. Okay. So this 11 kV bidirectional three-phase, active neutral clamp, neutral point clamped inverter actually GaN based. So this is what the industries, what they do is, they manufacture this, they make some kind of a model, they release into market. They don't release it as they release this as a reference design. So industries, we see that, this is a kind of thing is working, and then we'll make it possible also. And next is Wolfspeed. This is another one actually. This is also another very popular company. So SiC based power modules they started. I mean to say that all semiconductor companies now their companies they are into the market of gallium nitride silicon carbide. Okay, so this is a SiC based power module. So Infineon, another is very popular company actually with this semiconductor company. So they are also this way we'll get this gallium nitride silicon carbide. And then this is Infineon. This is one model actually where 3 kilowatt. So 3 kilowatt, so this is a bidirectional, PFC. So power factor correction model using the silicon carbide MOSFET, 650 volts and 3.3 kilowatt. This is 3.3 kilowatt is meant for the cars. It meant for the even two-wheeler. Two-wheeler you will get a one hour full charging. In case of car, 6 hours it will require. Normal 20 kilowatt battery. And then another Alpha Omega, this is another popular company. They have a discrete components you will also get in market like this. And then Silictron, this is one company. And then Sysord, this is another company. They manufacture. And okay. And Toshiba also this is into the market, silicon carbide. And then this Wen, okay, they have more than 20 years experience. This is also Quero, this is another one, power transistors and all. And then Renis is a very popular company, gallium nitride power discrete, the company. And then GAN Power is another company. They even you can see that fast chargers, even for mobiles and other things, So they come up with a GAN based, fast chargers actually. So for mobiles and desktops, and then laptops and all. Texas Instruments also you can go a lot of this wide bandgap devices based. developments they have. Their products are into the market now. And Infineon also they have. And then ST Microelectronics, very popular company, another company. So, okay, transistor. So this is ST Microelectronics. This is 30 kilowatt, silicon carbide MOSFET DC-DC converter for EV charging application. This is what the picture, reference design. So now we can have the schematic also here. And this is what here. Okay, so onboard charger actually. And the VINA rectifier, this is very popular from the literature. I think if you are working power electronics, you will get to know this VINA rectifier, this arrangement here, topology. So VINA rectifier also, they made a reference design is available, 30 kilowatt actually. Then this is a parallel LLC with a digital control actually. So parallel, you can see the two converters actually. And then this onboard charger, okay, DC-DC converter based on silicon carbide from Wolfspeed, okay. And then this is also interleaved boost converter, actually 60 kilowatt from this Wolfspeed. And where we can see that silicon carbide we can use inverter, DC-DC converter, onboard charger. With these are the three places where you can focus this applications of wide band semiconductor devices actually. And this is so this is also 1.2 K MHB. So silicon carbide gate drivers nowadays when market also separately gate drivers directly available. Now we have with switches and gate drivers is available, then our work is very much easy actually. So instead of gate drivers now. So I'm coming to end of my presentation. Let me finish in 5 minutes. Okay. So let us my discussion on this now my EV topic is over, and let us come to my some of the general topic may be useful for many faculty are in this webinar. Okay. So I want to tell you that there are 4 wings, particularly faculty research profile. One is paper publications, that is journals and conference book chapter. So next is IPR, that is patent and technology transfer, where we can focus. Another is funded projects, where we get projects from government, central government, state government, international industry. So another thing is consultancy startup, actually government projects and the industry projects, or you can make your own venture to make it launch your startup. So generally, apart from academics, the faculty can engage into the research. But these are the 4 domains is possible. But many of the young faculty, they are aware of only publication. But apart from publication, other 3 wings also available to us actually. And of course, technical writing skill is very much anything if you want to take up in research. So without technical, writing skills, we cannot be able to success as a good author or something like. And so these are some of the tips for the students, like how to execute a good academic or research product, even for young faculty. So these are strategy. Okay, if it is BTech project, MTech project, or PhD project, this is thing where we will follow area of work, problem to be shared, objective, data survey, state of art, scope of work, and a proposed plan, action plan, review, and all. Okay. And of course, you can do research in any ways, or project any kind of ways. One can do only modeling. Okay, I am very much interested in modeling with mathematics and differential integral equation. Then I will do my complete research on modeling. I will publish IEEE transaction. Okay, that way also you can do. One can do a design, development, simulation studies, analytical and critical study, control techniques, optimization techniques, comparative study, integration, external studies, then performance validation. If the system is ready-made, then you can do directly performance validation instead of going with all other actually. So one can do the simulation control, simulation optimization, like this also you can combine them. So this way one has to complete this project with using these trends actually. And the same things what we industry they also use in the product launch from starting. They start with the modeling and finally they do the performance validation. Same thing what we can also take up the work in this way. And tips for erasers, and I recommend generally open source, because most of the colleges they are not go with subscription with many journals. Right now I think Indian government is working with one nation, one subscription actually. I think through that some of the institutes getting benefited. Hopefully other institutes also in near future. And read the papers very carefully, understand technical language of the content. Okay, this is very much important. So people will struggle with writing of the content, so they are not able to understand that how to project your results. Okay, you do the work, you have simulation, but you need to understand how do you explain your results. And simply is you follow your reference paper. So how the previous author explained your results, same way you have to explain. It's simple. And you have to choose your mentor. Okay, and then select a research area at the beginner. So with the minimum or no extra mentor.
So because you don't have facilities, you don't have any kind of tools or something, proprietary or something, then definitely you should start with your research with a minimum or no experimental. Then later, based on the college facilities and all, get into with facilities. They execute the work with open source tools instead of depending on nowadays every proprietary software or tool. There's other alternative open source tools are there. We can execute that. Okay, that way you can execute the work. And publications only scope of a Web of Science, because recently as a government also we done UGC care list, and they are bringing a new one, and then many places they are recognizing only scope of Web of Science journals only. Other journals they don't consider them. And publishing, I personally recommend IEEE because IEEE conferences, even though money is there for a registration, but you will get a citations. Okay, because other conferences you don't get citations, because IEEE your conference papers and journal papers are maintain the same digital explorer. Okay, then when the people are search for any kind of material, then they will also quote your reference paper, conference paper also. It's so that you will get a citation. Okay, you may not having IEEE journals, but you have IEEE conference only, but you will get a good citations. Okay, that will improve your H index also for your personal profile. So these are the types of open source and software coding is available. Server, some limitation up to server usage also. Some open source is a hardware also. And using open source, you can free to use, free to share, free to change, sell to work also. And to become extraordinary, one has to exhibit this out-of-box thinking for problem solving. This is what in the research and academic also from students also we expect that. Is it right? So we give problem statement for everyone, but there is one student, one faculty, one engineer will come with out-of-box thinking. He will make the solution as very compact and optimized. Is it right? Maybe instead of 10 line, 100 line program, he'll come with a solution with only 10 line. Then he is very extraordinary. So don't be ordinary. Okay, in the executing of things, academic and research, you should execute this out-of-box. And finally, 3 important learnings, very much important for all professional education or career. One is continuous learning. So without continuous learning, what will happen? You will be outdated. Even we are not fit for the faculty jobs, or even we are the engineers also, they are not fit for their core engineering, because technology is upgrading. That's why this workshop also now focuses on WBG. Is it right? And then self-learning. So till graduation for students, there are teachers are there in the department to teach. After graduation, who is there to teach them? Is it right? Everything is self-learning. For faculty or engineers, everything is self-learning process. From the students stage itself, they have to habituate to the self-learning process. And finally, global learning. Whatever developments, whatever learning here, and it's applicable to anywhere in the globe. So we are also taking from global, applying to local. From the local, we need to apply to global also. So that's a global. And this is my last slide, final slide. So opportunity types. So opportunity will come and knock your door. Okay. So generally what we should do, we should open the door and see whether it is useful or connecting with me, grab it. If it is not useful, then I will. But sometimes students particularly, they don't open the door. They don't see that, because opportunity may come in any kind of, they may come in some phone call, message, email, WhatsApp, whatever way, even some advertisement. We should not neglect any opportunity. And sometimes you need to search for long, to spend time, and then you need to travel. Maybe it is job or any kind of resources also. So then you need to see. And sometimes call for opportunity, you need to come forward and apply. Either a particular jobs, okay, particular project grants or something for faculty. Is it right? So you need to come forward and apply. Otherwise, nobody will come and to home and then give you the opportunity. Is it right? So then fourth one, plenty of opportunities around you always, but those are invisible, but you should identify and grab them. Suppose we may think that students, so I wanted to get some machine learning for my electrical EV vehicle or renewable energy. You may think that, maybe no faculty in the department, they are not export machine learning. But there are faculty. Nobody keep some board on the notice board or something, we are expert in machine learning. Is it right? So, but your duty, you should identify them within the department, within the surrounding itself, and you should interact with them and get the opportunity. So these are sometimes invisible, but your duty, you should responsible, you should make them identify. And last one, sometimes call for opportunity, first come, first survey based. So limited it. Maybe sometimes the workshop is offline, so very limited, 30%, 30, 50. And cinema hall, seats are limited, buses, seats are limited, train, reservation is limited. Is it right? So always, don't be, last minute, last 11th hour, last day application. So don't be do that actually in a professional career actually for students and faculty and that. So you should be always possibly always, you have, very good opportunities will be there actually. So thank you. With this, I will conclude my, so once again, I thank Mahalingam College of Engineering, Tamil Nadu for giving this opportunity. So thank you very much. Yeah. I also thank the participant for patient listening. Thank you.
Thank you, Dr. Sandeep. Thanks for your very informative session on EVs, Wide-Bandgap semiconductors. Participants, if you have any doubts, please ask the doubt by putting your mic and unmute your mic. So I see someone has participants, if you have any doubts, please unmute your mic and you can ask. Or you can put your comments in the chat section.
Yeah, I shared my email and mobile number also. If any participant, if any future interactions and all, they can contact me directly, no issue. Many interactions also, it happened like this actually. So even project collaborations and all, and kind of, any other future events and all. I think many people, they interacted with me like this, not a problem.
We can wait for 1 more minute so that if someone can ask the question.
Sure,
I
sir.
see. Yeah.
Sure.
Wait a second.
Yeah, can we did the collaboration in terms of lecture on the electric vehicle? Yes, sir. Yeah, we can do, sir. I shared my email address, phone number, sir. Please, we'll connect. Yes, sir. We'll connect separately. Yeah. Also, if
Sir,
anybody from
Sandeep, sir.
industry, and we have one DSR. Yes, sir. Yes.
Okay, sir. Okay, go ahead, sir. Go ahead, sir.
Yeah, what I'm telling that, we have one DSR funded project actually where we work on renewable energy and electric vehicle. And if you are working with industry problems, and particularly if you are already your college, or if you are from industry or startups or something, MSMEs particularly, and we can able to directly collaborate actually. Okay, so it's a part of, the center is part of NIT Andhra Pradesh. Okay, you can go to our website. Okay, so let me share that link also now. Let me do that. So if we kind of, any problem statement from industry, and if you are already working with MSME, okay, so then this is a platform where we are working with MSMEs actually. Okay, and renewable energy electric vehicle, so where we will collaborate and then directly work on their problem statements actually. So that is one thing. Let me share my, yeah.
Tony sir, do you have any questions?
Yes,
I
sir. I
shared
have a
that
question, sir.
website link also. Yes, please.
Sir, I will share it, sir. Then I'll ask the questions.
Yes,
Yeah,
sir.
we
I
got
shared the web link of that. Yes. Thank you.
Okay, sir. Sir, I have a question, personal question, sir.
Yes,
Nowadays,
yes, please.
getting through papers, standard papers out of in doing the novel converters and things, sir. I'm actually a researcher in making novel converters, sir. It is me a very tough task for us. Can you please suggest me that how can I change my view of making a novel converter to get placed in a good journal, sir?
Yeah, one thing is, what is simple task, already based on this workshop itself. Okay, now we got the very good knowledge on this, wide band gap devices, particularly GaN and silicon carbide. So whatever work previously done with, say, MOSFET and IGBT, even previously if you look at, MOSFET work was replaced with IGBT. Is it right? So same now, whatever the work done with MOSFETs and IGBT, that can be same with replaced with, GaN and silicon carbide. Then we can do the same research. You can repeat the work and then you will get a new results and better performance, and you can make a publication again. That's a simple one. Okay. Okay. That's a simple. And apart from that, I also listed one. Sorry.
Tell me, sir. Yes, sir. Tell me, sir.
Yeah. So that is one thing. That is simple one actually. So whatever now previously, let us take one topic application based on what they implemented based on IGBT. Now replace with this as a SiC based devices. That's one thing. And the second part is also I given one slide actually. Anyway, I'm sharing my slides also. So one power electronics based research actually. One is you need to see first is application is very much important. Okay, power electronics. Okay. So based on the application, definitely we'll get a new ideas. Okay, algorithms. People are coming with the new algorithms. Okay, we have you propose one algorithm, I propose one, but actually again application also we can slightly modify. So okay, maybe there is some application where that is kind of one stage of monitoring. So you wanted to bring the next stage of monitoring. Okay, then definitely I need to change the algorithm also. So that is one thing. Always we have a scope in algorithm. And coming to physical structure of the power electronic circuit topology, we have always challenged. That's why people are now coming with a reduced switch topology and all. But very very difficult task it is actually. So that is one thing. Okay. So these are the three, areas where you can start it actually. And also integration of the things also. Integration in the sense, two parts, maybe one they propose one application where you can combine with other. Okay, for example, like solar is there. Now solar and wind. So you can combine them and make the microgrid. That is possible. That is one thing I can give another idea. And then, another part is, yeah. I forgot. Yeah.
Thank you, sir. Thank you very much for your guidance, sir.
Yeah. Thank you. Yeah. Yeah.
Hello.
Yes, please.
Okay, so my question is related to the battery balancing in EVs. Okay, I think this is a very difficult task to balance the
Yes,
cells in the
yes,
lithium-ion batteries. So,
correct.
which kinds of the theories or the technologies are basically used in the industries in practical domain?
Okay. Yes, yes. Actually, this is a part of BMS, battery management system. Cell balancing is the one very much important. One is, it will come as a pack, but actually, in the pack, we need to see the each cell, voltages, whether it is balanced or not. So one is, there are, we have kind of, algorithms, okay, even as a part of, SOC and SOH calculation, and we need to predict the voltages of the each cell actually, okay. And then in that case, we have we have to replace with the damaged battery cells and then replace with the new one actually. So these are things are very much important. So but industry SOC point of view, extended Kalman filter method is now getting very popular actually. They are using that actually. And we need to see that there is one challenge is there. So if you are using one voltage, okay, that is okay. Overall voltage of the battery pack and then current and temperature. If you sense these three parameters, you can find the SOC. There is no problem. But what you are asking is cell balance. That means each cell voltage you need to get it this thing. For which what they do is people industry people, they have the kind of setup where they can measure the each cell voltage. But for academic researchers, that kind of setup generally it is not available with us. It's a very much challenge to us actually.
Okay, so research is possible or not in this particular sector?
Possible. For which what we do, I suggest you, let us make some kind of small 500 watt or 1 kW battery pack. Okay, let us buy individually cells. Okay, lithium,
sir.
lithium
I will
component
contact
cells,
you.
and then connect them as yes, yes, yes.
I will contact you regarding
You
this.
can I give my email. Yeah, you can.
Okay, sir. Thank you.
Yes, please. Thank you.
Sahib, raise your hand. Can you unmute and ask the question? Okay, I think, Professor, we have come to an end. So we have,
Okay.
yeah.
Okay, sir.
Professor,
Please.
one more. Again, I thank you for your wonderful presentation and informative information shared with us. Thanks for your time and information. Thank you, Professor. And thank you all the participants for joining us for this seminar. Thank you.
Yeah. Thank you all. Thank you all. Yeah.
Thank you, Professor. Yeah.
Thank you so much, participants. Thank you, sir, as well. You can please fill the feedback form. If you have filled the feedback form, you can take a leave. Thank you very much. Thank you, Sam, sir, for being with us. Thank you very much, sir.